Hello everybody, I'm back again to talk more about free energy. We'll be talking about today the relationships between the thermodynamic state function G, both just delta G under any circumstances, as well as delta G naught or delta G superscript 0, which is for standard state conditions. With the equilibrium constant K, not to be confused with the rate constant, also with a K. Unfortunately, we run out of symbols in these courses. That's one of the common problems, and I will specify which version of the equilibrium constant it is as we go along. There's a relationship. I will not derive it in this course. It entails things that go beyond general chemistry. I would derive this in physical chemistry, for example. At an upper division course. You could even derive this in a grad level course. It's actually a straightforward derivation, but it involves something called chemical potential we really don't talk about in general chemistry. But this is a relationship that links together delta G is not meaning for the standard, and Q, this is the reaction quotient. Can't spell. But this is a very general broad spectrum equation. You can use it. R here in this case is the gas constant in the joule per mole Kelvin form. And of course this is temperature in Kelvin. I'll write Kelvin out so we don't have another K on the board. And so you could get this in, you can calculate delta G using this relationship here. But before we do anything with that, let's just think about the case at equilibrium. I'll just call equilibrium EQ. At equilibrium, recall from our prior free energy discussion, delta G is equal to 0. So in that case, we have 0 here. Delta G naught, nothing happens to the R and T. But then Q at equilibrium becomes K, right? That's Q is for anywhere along a reaction coordinate. The specific spot that we call equilibrium, we use a different symbol for that, and so we call that, that'll become ln of K. So you can write a relationship, delta G naught is equal to negative RT ln of K. That's a perfectly good equation. That's one I would definitely give you on an exam, for example. But let's just talk about this. To make this equation work correctly, there's a rule, and it has to do with the way that we've derived K from activities, which we don't go into here. But when you do the gas phase, if this is a gas phase reaction, use Kp. If you're meaning with this will be formed with the partial pressures. If you're doing aqueous phase or other solution type of calculation, for primarily we'll do aqueous phase, use Kc. In both cases, use the R, that's 8.314 joules per mole Kelvin. Temperature will be in Kelvin, of course. So that's something to take note of. Delta G in that case will come out in units of joules per mole. If sometimes you might have to convert that to kilojoules. Kilojoules often is just nicer for the scaling of the numbers, but you can do that at the end or build the factor in there. But that's the big thing over here in terms of usage for this equation. We'll talk about the interpretation of it in a second, but that's an important equation that ties together the equilibrium constant K, whether it be Kp or Kc, doesn't really make a difference, with delta G naught. It's a very foundational relationship. Let's talk about the interpretation of this in terms of why this equation matters. I'll leave that equation up. We can always write the other one back down when we need it. Got my soccer racer here. I'm making this video at about midnight. If you hear weird noises outside, that is my raccoon friends hanging out. I don't know what season it is, but they're making extra strange noises tonight. So this is on page 12 going into 13. Let's talk about some interpretations. Whether it be Kp or Kc, it doesn't make a difference. When the equilibrium constant is greater than 1, well then let's look at this, what this means. That means ln of k is greater than 1, which means there's a negative out here, right? So we got a negative. That means delta G naught is less than 0. So for a reaction like AA plus BB going to CC plus DD, what that means is when you form it under standard conditions, that would be in the case of if this was a gas phase reaction, everything at 1 atmosphere. If you read some sources, they'll say 1 bar. We'll stick with the 1 atmosphere interpretation. If it's in solution, everything's at 1 molar concentration. If you form it like that, what happens is saying from that point of reference, the reaction's going to shift towards product. It's spontaneous in that direction. It's spontaneous to the right. Think of this as this was just had an arrow going to the right. Delta G less than 0 means spontaneous to the right. And so it's what this does is this relationship allows us to say, well, is the reaction spontaneous or not? We have a reference point to say spontaneous relative to what? And so we say, well, spontaneous relative to, if you were presented the system in standard conditions, would it move to the right or the left? In this case, it moves to the right. It moves, we could say, towards products. If we formed this system, let's say this was in the gas phase, and this was 1 atmosphere, 1 atmosphere, 1 atmosphere, 1 atmosphere, it would head to more C and D relative towards A and B. And so that's one condition. And these are the type of things where I can ask qualitative questions like in the multiple choice over, so the concepts are important. In case number 2, k less than 1, then the ln of k is less than 1. If you don't believe me, just draw a graph of it or verify it on your calculator. Negative of a negative gives you delta G naught greater than 0. The interpretation of that is heads to the left. It heads towards reactants. You can imagine it like this, is the way you go. One of the ways you can think about it is if you flip this reaction around, you can flip around the sign of delta G, and then it would be spontaneous. It would be less than 0, it would be heading to the right, but you flip this around, you have A and B on the right-hand side. But at any rate, that's one way of interpreting it. You could also think if you have a reversible reaction and your delta G or your delta G standard is negative in the one direction, it's spontaneous to the right. If it's positive, it's spontaneous to the left. So that's another interpretation of it for a reversible reaction. We usually define a reaction as going to the right, but in these cases we have a reversible reaction. So what we interpret as products and reactants is merely our vantage point from how we write it. So because it is a reversible entity, I could write this flipped around, but I would have to acknowledge it's flipped around. So then there's the third case, which is actually kind of trivial, which is k is equal to 1, and that means that means ln of k is 0, and that means delta G naught is 0. The interpretation of that is that reaction is at equilibrium under the standard state conditions. I put that in for completeness. Very rarely is k going to be precisely equal to 1. It's just another number. K is equal to 1 is no more better than saying k is equal to 14 or 10 to the 1 times 2.2 times 10 to the minus 7. It's just another number. So this would be a special case. Does it exist? I don't know. There's probably some reaction out there where k equals 1. It's precisely at equilibrium. But certainly if it's close to 1, it's in vicinity of that, so the system's not going to make much of a change to the left or right. So this is, again, this is a conceptual thing where understanding these point of references, particularly these two, gives you an orientation of what direction the reaction would head relative to something we all agree upon, which is standard state conditions. So that's good to know qualitatively. So we have these two equations. Let me erase all this here. Now at this point I'm going to do a problem I have a really good one in the notes on page 13 in the skill builder. I'll work it out. What I suggest is if you're wanting to work a good problem like this, turn off the video now, and then I will post the solutions of all these, but it's a little different if you work it out on your own. Work it out on your own and come back and look at the video. Maybe I made a mistake. You can find something I did wrong. That's always fun to do. And then I'll either correct it or put a note in the description. Sometimes, I make a numerical mistake. This is actually a problem that's in the book. If you do have a textbook, it's problem 1647 out of Overby. But if you don't, it's fine because I have a problem right out here. It's just one that I had good numbers for. So, again, if you want to pause the video now, it's perfectly fine. I won't know. So, we have a gas phase reaction, PCl5. There's a lot of P's in this problem. Gas going to PCl3. Gas, all gases, and Cl2 gas. We have that. So make sure I can read it down here. Yeah, we're in this full view. And so they tell us let's focus on 25 degrees Celsius. And we want to know what delta G naught is and K sub P for this gas phase reaction. And once we have Kp, if we didn't want to know Kc, we could always convert it, right? We have that conversion relationship here. We have delta N is 2 minus 1. It's 1. It would be a straightforward conversion. We know the temperature. So this will pull some skills together. So we can use our relationships. We're going to use delta G naught is equal to negative RT ln of K. And there's a part 2 to this problem, I believe, as well. Maybe there is, maybe there isn't. So part A is that. And then there's a part B to the problem where we have some different conditions, and we'll calculate out from partial pressures delta G for a system that's not necessarily in equilibrium. So let's do the first part. This would be part A of the problem. So we're going to use the relationship delta G naught is equal to negative RT ln of K. In this case, I'll write it, this is K sub P. So what our game plan is first we don't know what K sub P is. We're not presumed here to be looking that up. That's kind of like a cheat. That's not the purpose here, is to go Google what we're going to do it from fundamentals. So what we will look up is we will use this formula delta G naught is equal to, you're summing over the products. You will use the delta G as a formation for them of the products. This was from the chapter on free energy and entropy. Over the reactants, we'll look up delta G formation of those. I'm using the tables similar, I believe, to the or identical to the ones online that are thermo tables. If you see like a number like I have here negative 267.8 kilojoules, and you look in the back of a source and it says negative 269 or something, that's just, the tables will vary slightly depending on your source. These are experimental values, but this, I believe, is from the table, the thermo tables that you should have available online. So let's look up, I look up some delta G values. For the Cl2, that's the elemental form of it, and so the elemental form, delta G naught, a formation that is the most stable form of chlorine at 25 degrees Celsius. And so that's the delta G formation of the chlorine is a big old 0. And for the PCl3, it's 267, negative 267, that would make a difference, 0.8 kilojoules per mole. And I'm just writing it over just so we have point of reference. And for the PCl5, it's negative 305.0 kilojoules per mole, just to have something to write. So the way this formula is going to look is we're going to have products. So we're going to have the delta G is going to be equal to there's a 1 in front of these, so these ends of P's and ends of R's are trivial. We're going to have negative 267.8 kilojoules per mole for this species. We have a 0, I'll just write it in for goodness, for the Cl2. Then we have a minus. I'm going to put it like this because it's a real easy trap. I probably made the mistake when I do this on a piece of scrap paper. It's real easy to forget the negative of a negative. That's kind of like, I'll put a little asterisk here. Even I make that mistake all the time. That's, I see that on an exam. I go, that's a 1 point off on a problem that's 10 points. I look at that as a small mistake. Like, I make that mistake all the time. So we have 37.2 kilojoules per mole. Again, if we didn't have that in here, we'd be way off. We'd have a big negative number in the mid 500 kilojoule per mole range, so we'd be like way off. So, this is sometimes you get wacky numbers, but you didn't do anything that bad. So we have this equation. Let's manipulate it to put it in form of Kp. So ln of Kp is going to be delta, this will be a negative here, delta G naught, so we're going to have a negative built in, RT, right? And then this is, again, the natural log, the base of it is the exponential E. So we're going to have E, well, I'll write it like this. Got to be real careful with the board. I'm just, it's just propped up on my kitchen here on the cupboard. So that's the form of it, so you should feel comfortable doing that manipulation. Have to have everything in common units here. Make sure we have, this is in kilojoules per mole. So this is another thing, is pay attention to units, because we got kilojoules per mole and R, we're going to pull it off a table in terms of joules, unless you're using some different table I'm not familiar with. So let's write this as 37.2 times 10 to the 3 joules per mole. We have R, 8 this is all in the exponential, 314 joules mole Kelvin. And then convert that to 298. We got 25 degrees, add 273 to it. If you want real accuracy, put 0.15 after it, but wasn't that accurate, so we have 298 Kelvin. To the best of my calculation, I got 3.01 times 10 to the minus 7. See if you get that number. I would do the exponential, do this first, and then plug it into the exponential. It's real easy when you're on your calculator and you have something raised up. Don't forget the negative. And the big thing here, again, is you got joules per mole and you got joules per mole, Kelvin. So this has to have no units when you're all said and done on the inside. The argument of the exponential is dimensionless. And so that's the answer for the first part. We got Kp, I'll write it over here, keep this retained. So, we got delta G naught. And we got Kp. Now there's another problem. That's part A. Let's go on real quickly, do part B. We have this reaction, and I want to relieve these two things here. I have a board for this, but my best lighting is on the spot right where I'm at, and I can't really fit the board in here, so I just have this thing kind of propped on my cabinet. So it's crude, but it works. The second part, it says calculate delta G. So delta G is under arbitrary conditions, and what we have is that we're told that the pressure of PCl5 is 0.0029 atmospheres, and we're told that PCl3, this is the pressure of PCl3, is in 0.27 atmospheres, And this is all written in notes if you can't read my writing that well. This is on page 14. And the pressure of the chlorine gas is 0.40. That's terrible looking 40. 0.40 atmospheres. So what do? We're going to use the equation delta G is equal to delta G naught plus RT ln of Q. Atmospheres is good. If it wasn't, we would convert it. So what do we do here? Let's Q. Well, I'll just do it out. We can just do it in one step here. You can do it off to the side if you care to. Delta G naught, did we erase that? Yeah, we did. That's 37.2 kilojoules per mole. So here we got this. They want the answer in kilojoules per mole. So we'll convert the R. We've got 8.314 joules mole Kelvin for R. Let's convert that. There's 1,000 joules or 10 to the 3 joules per 1 kilojoule. Now we have kilojoules. And then we have temperature. Again, we have it in 298 Kelvin already. We have to have that in Kelvin. And then we have ln of Q. Q's products over reactants, right? So let's fill it in. Products. We got Cl2.40 times, everything's to the first power, PCl3, 0.27. That's in the numerator, products, and in the denominator, what do we got here? 0.0029. So what I got when it was all said and done, you probably want to do that and then plug in the ln and multiply it by the coefficient. You can do it in stages. Confirm that you get 46.1 kilojoules per mole. The interpretation of that is that's greater than 0, right? It's a positive number. It's going to shift left. It's going to head towards the reactant species, the PCl5. And so that's what it's going to do. So check that out. Compare Q to K and see if that makes sense. Is Q greater than or less than K? And rationalize your answer based on that. So on that note, that's a good problem. And if you've worked it on your own, you're coming in. If I made a mistake, let me know. It's sometimes people say you made a mistake and they don't tell me till like a month later. I'm like, I have mild dyslexia. I can invert a number all the time. So at any rate, we're going along good here with chapter 16. We'll keep trucking along and making about 3 videos a day here. So we'll continue on this topic tomorrow. Take care.